So, we continue with our discussion on VC dimension as related to construction of Epsilon-Nets. Just to recap what we did yesterday, yesterday in the last lecture. Okay, so we went through some formal definitions of VC dimensions and range spaces. Well, we started with the range space X R, where X is a set of points and R is a set of family of subsets, and the notation that we used that when Y is a subset of X, then the range space restricted to Y was defined as Y comma ranges restricted to Y, which is nothing but the subsets of Y in that is the intersection of Y with the ranges of original ranges, right. So, this helps us take care of the situation where Y is finite, as in the original definition of range space X may not be finite. Okay. So, if Y is finite, then everything becomes finite, right. Then you have the set of points to be finite, and also you have a finite number of ranges, right. Okay. And then we had seen some examples, natural examples of range spaces, and in particular we went through this definition of VC dimension, which was defined on the basis of what is called shatter. So a finite set Y cannot be shattered if the other way around. So, a finite set of points can be shattered if you have subsets or the number of ranges in the range space is equal to the power set of the set of points, right. So, every possible subset of the given set Y has a corresponding range. Okay. So, that is when we say a set of points is shattered. Okay. The maximum number of points that can be shattered, okay, is called the VC dimension of the range space. Okay. And we actually saw situations where the VC dimension, well, a simple example like intervals and points in the line is when you can't shatter a set of 3 points, because you can never include the 2 boundary points and not include the internal points. You can't shatter a set of 3 points in a line using intervals, right? You need something more than that. So, but range spaces are always defined that a VC dimension is defined with respect to the kind of ranges that goes along with the range space. So, for intervals we cannot shatter even 3 points, which means that according to the definition and of course, we can shatter a pair of points on the line. So, therefore, the VC dimension of this is 2. And we saw some other examples where this range spaces were defined by the set of points in the plane and all the convex subsets. Now, this is a classical example where the VC dimension is not even bounded, because I can take a set of points on the if the points are basically on the convex hull. Okay. So, all the points are on the convex hull, then I can capture any subset of the points using convex subsets, because the subset of a convex polygon is also convex, right. Any subset of a convex polygon, and the points defining the convex polygon is also convex. Okay. So, this is an example where you do not even have finite VC dimension, right. But our interest is in those range spaces where VC dimension is finite, so that we can define certain other combinatorial properties with respect to VC dimension. Okay. So, this is where we concluded our last lecture, and the overall motivation was this, that if we somehow we will be able to prove the following property, that if we are trying to form a set cover of the so called large subsets, okay, and this set system or the range space corresponding to the set system has a finite VC dimension, then somehow the size of the set cover, okay, can be captured only as a function of what is called the epsilon, that is, we are trying to cover all sets, okay, which are of size at least epsilon times n. Right. So normally, if you do just some simple random sampling, then you'll get an extra log of n factor as the size of the set cover that you require to hit all subsets of size at least epsilon n. Right. But as we'll see, possibly tomorrow, maybe the next lecture, that when we have finite VC dimension, we'll be able to actually show the existence of set covers whose size do not depend on the number of subsets. It's only dependent on the epsilon. Okay, so we'll need a few more definitions and some more concepts of range spaces. Okay, so let's continue with that. Okay, so the first thing that again I will define today is a slight variation on the definition of what we discussed in the context of shattering a set of points. Okay, so here is another definition of a twist on the shatter. Okay, and that is called the shatter function. Okay, so for the range space is equal to x comma r. So, B is a finite subset of size m. Okay. So, look at all finite subsets of size m, and we are maximizing on the number of ranges restricted to subsets of size p. Right. So, you for any m, okay, look at the number of ranges. Okay, look at the number of ranges of the worst possible subset of size m. So, maximize the number of ranges for any subset of size m. Okay. And this pi s of m, okay, for every m, when you set it to the maximum of this quantity, that is called the shatter function. Okay. So, for different m, it could take different values depending on the configuration of the point. Okay. So, for maybe for m equal to 2, it will be 5, maybe m equal to 5, it will be like 20 or whatever, depends on what is the worst configuration of size m that leads to the maximum number of ranges, right, maximum number of possible subsets, okay, as defined by the range space. All right. So, this is the shattering function and the shattering dimension. Okay. So, now there is a subtle difference between the shattering dimension and the VC dimension. Okay. So, what is the shattering dimension? Is the smallest d such that pi s. So, this shatter function can be bounded by some kind of polynomial.
So, what does R to the substitute B means?
are restricted to B. This is what we had defined before in the last lecture. So, you look at all the ranges. Okay, so this is nothing but okay, this is nothing but all those R intersection B such that R belongs to the original range space. So, we are not only talking about subsets of B, that is all. So, we defined the shatter function like this, and now we are saying that the shattering dimension of S, of this range space S, is such that we want to somehow bound it, although it was not clear from the definition of VC dimension. That is what are we looking at? We are looking at only the power set, right. So, we say that beyond this some size of some VC dimension, some size delta, okay, we can't really generate the power set using the ranges. Right. So, but the power set is basically exponential, right, 2 to the power delta. Now, just because it is not exponential also does not imply that things should become polynomial, right. Suppose my VC dimension is 10, okay, which means that if there is some subset of size 10 such that I have ranges from the range space that can generate all subsets of this configuration of 10 points, okay, that is 2 to the power 10. Now, when I go to 11, 12, 13, whatever, I know that I can't shatter those because my VC dimension is 10. Okay, I can't shatter a subset of 11 points or 12 points or whatever, okay, which means that I can't generate all the 2 to the power 11 subsets, or I can't generate all the 2 to the power 12 or whatever. Okay. But it does not say anything about that it should be polynomial, right. It is only that we can't generate the power set. Right. But then what turns out, and that's very surprising thing, that once we once we can't shatter something, okay, it turns out that after that we'll give a proof of that, it turns out that then we can kind of bound the number of subsets that we can generate using the ranges by a polynomial. That is eventually what we'll prove, okay. And in that process I gave another intermediate definition of a shattering dimension, okay. So, shattering dimension says that you look at the worst case configuration, okay, so that you are looking at the maximum number of subsets that can be generated for that worst case configuration of size m, that defines my shattering function, okay. Now, that shattering function, if I can bound by some polynomial, okay, m to the power d, where d is some fixed constant, could be very large, okay, then that is called the shattering dimension of S. The shattering dimension of S is not necessarily the VC dimension. The shattering dimension is by definition something so that it will help us, or it is supposed to help us, bound the number of subsets that we can generate by some kind of polynomial. It is not even clear from this definition that the shattering dimension actually exists, that there is such a d. It says that find the smallest d such that this is true. There may not be such a d, right? It is just a definition at this point.
So, for some sets the d, I mean, they can be infinite, shattering dimension can be infinite?
Yeah, it can be. You will see the VC dimension is infinite, the shattering dimension can also be infinite. Clearly, where the VC dimension is infinite, the shattering dimension is also going to be infinite.
So, can you give an example of this and given a point set or kind of thing and show how to compute the shattering dimension?
Yeah, so I will do that. In fact, I have done that already. If you just recollect, what we did for trapezoidal maps, what did we do? We are basically defining some kind of bunches of segments that we can get by from a sample. So, we looked at the segments, selected some of them, okay, there are those defined trapezoids, right. So, if my ranges are trapezoids, for example, so if we look at this range space where my x is a set of segments on the plane and my subsets are trapezoids, okay, trapezoids of where the parallel sides are parallel to the y axis. So, that is a range space, okay, where we were actually generating these subsets, the possible subsets of the segments, right. Each trapezoid captured some segments, okay, and we already if you recall, it is a very simple argument that because a trapezoid has to be defined by at least 4 segments, okay, then there are maximum of n to the power 4 possible trapezoids, right? And those are the only distinct subsets that you can have. So, you see that already we have this n to the power d is 4 there. Okay. So, we have an argument for the range space where S is a set of segments and the subset are trapezoids, where the shattering dimension is 4. Okay. Now, it is also a non-trivial problem. Many cases, for many range spaces, what is the VC dimension? Right. So, we will also look at maybe shattering dimension is sometimes easier to compute, and if you can find a relationship between shattering dimension and VC dimension, then maybe we can get a bound on the VC dimension. That is the other motivation for the definition.
So, is computing these two quantities, VC dimension and shattering dimension, NPR?
Oh no, this is not a computational problem, it is a purely combinatorial quantity. So, we are not trying to discuss algorithms to compute this. No. These are just combinatorial quantities.
But you have to determine something, right?
Yeah, determines, so we have to determine. It is not an algorithmic, we are not trying to determine the VC dimension algorithmically. It is given a range space, tell me what is the VC dimension, by whatever proof techniques you may have, or if you do not have, or maybe you do not have a very tight bound, you can only say VC dimension less than 100, but I do not know whether it is 90 or 91 or whatever. Right? Same thing about shattering dimension, I am saying it is 4, but maybe it is less, who knows. Right? But our requirements, or we are not really looking for very tight bounds, we are only kind of looking at situations where we can get a finite bound on the VC dimension, because most of our arguments will hinge upon the finiteness of the VC dimension and nothing more than that. Right. So, the shattering dimension somehow manages to bound this function by some polynomial. Right. And VC dimension definition does not say that if we can't shatter a subset, we can actually bound the number of subsets by polynomial. It does not say that. It only says that okay, if we can't bound it by if we can't generate the power set, then we have found the VC dimension. That is all. Right. So, let us see if there is a connection between we will see some connection between shattering dimension, VC dimension, and why that is the surprising part. Here it is so that if it is not the power set, then it becomes some kind of a polynomial. Okay, that is the bound we will try to prove. Okay, so for that there is a nice technical lemma. So, it is called Sawyer's lemma. I think various people proved it, but it goes by the name of Sawyer's lemma. So, if S is equal to XR as VC dimension. Okay. So, I am trying to use consistently delta for VC dimension and D for shattering dimension. Right. Okay. So, now comes the punchline. Suddenly, we are saying that now we are claiming that if the VC dimension is delta, okay, then and we have a set of points, finite set of points x of size n, then the maximum number of ranges is n to the power delta. Okay. So, suddenly from 2 to the power something, which was a power set, now we are talking about n to the power delta. And in fact, more precisely, so this one more precisely, it is bounded by some function g delta of n. It is a familiar looking function actually, n choose I. So, all possible ways of choosing delta or fewer objects from from n objects. And just as a remark, and we will use that property for the proof, G delta n is G delta minus 1 n minus 1 plus G delta minus 1, right? The familiar recurrence for choosing n objects from delta objects from n objects. So, either we choose the so we have not chosen, missed something. So either we choose the nth object or we do not choose the nth object, right. So, if we chosen the nth object, so then I have to choose delta minus 1, that is fine, and in other case I just, in both cases it should be n minus 1, right. In one case I have not chosen, in one case I have chosen, right. This I will just will plug somewhere in the proof, actually into the proof. Okay. So, this is called Sawyer's lemma. Okay. How do you prove it? You prove by induction. Okay. I will not write the induction statement, proof by induction on delta n. So, there is a double induction basically, there are two variables delta and n, right. So, suppose true. Two. Okay, actually, since I am not writing the induction statement, there is a slight danger. So, we are saying true for all values till delta minus 1, all values of n till delta minus 1, and true for all values. Okay, what do? We define two. So, from the given range space, S is equal to x r. Okay, we define. So, for a fixed x, okay, we for a fixed x, we define Rx r such that x does not belong to R and R union x belongs to the range. And R. So, I am defining two ranges from the original range R. Okay. And this is, so I am kind of throwing out x from the ranges. Okay. So, such that So these are the two things that I have defined. It is not a good place to define this. So let me just make a note here, because we'll have to stare at this thing for a while. So Rx okay. So there is this original range space R, okay, and look at this R minus X. Okay. So there are these ranges here and there are some ranges here. Now, can we define some kind of mapping between R and R minus X? See, X may or may not belong to the range, right? So if X does not belong to the range, okay, so this one has a easy counterpart here, right? So if X does not belong to R, right? It is an easy it doesn't belong to R, so R minus X and R are the same. The trouble is that if X belongs to R, right? So if X belongs to R, so this one, X belongs to R, okay, then it is mapped to again something which takes out this. Okay, so maybe it's mapped somewhere. Okay, so maybe it's mapped somewhere. X belongs to R, and I am mapping it to something where I am taking out X from there, right? The trouble happens when X belongs to R, okay, and so both of these, when they get mapped to the same one, then we may have trouble, right? So we are trying to have a kind of a would like to prove this thing. Okay, let me tell you what we are trying to do. We are trying to prove this. The number of ranges R is equal to this plus this. Okay. So I am now trying to look at the cardinality of R minus X and R. Okay. So when X does not belong to R, then it has a counterpart. Okay. Now X belongs to R, okay, is mapped somewhere, but something else also may be mapped here, right? Maybe how can these two things get mapped here? So both of them may get mapped here. When does it happen?
When two ranges have one point X, two ranges are overall same but have an extra point X on the ranges.
The second map is to a set that doesn't have X.
Yeah. So you have a range, okay, such that X, in some sense, X, there is a range in R such that this and this, both of them are mapped to the same. So the R union X also belongs to R, and taking out X, that also belongs to R. Right? Both of the ranges will get mapped to the same range in R. Right? If both of them are getting mapped, it means that this range, okay, even without X, okay, and this has the X, so both of them are getting mapped here. So both those ranges. So X, it is precisely this. When x does not belong to R, okay, so this R and this R, both of them belong to the range, original range.
So won't it be in the other manner, sir? Two of ranges from R will get to map to a single range in R minus x.
Oh, am I doing it the other way around? Just a moment. So, I am just trying to find the correspondence between R and R minus x. So, R minus x, oh, I see what you are saying. So, it should be the other way around?
But it can be,
No, no, it, huh?
it can be this way also.
Is it Rx then? Rx?
No, no, Rx we are not touching. We are only looking at this one. Rx will basically, make sure that this happens. That's all. Rx is precisely those elements where this is happening.
Otherwise, the dimensions of R will be less than R minus x.
Yeah.
Both is
Is the argument easier to go in the other direction? So, R minus x, okay. So, will it be easier? Okay, let me try another thing. Just
There is xyz, there is yz in R. If R minus x is yz.
so, I think it will be easier to argue this way, R and R minus x. So, yes, I mean for if x does not belong to R, there is an easy mapping. Okay. And so, there is some range, let us say this is R prime, let us say R double prime. So, this got mapped here, okay, and if this is equal to R prime, that is what you are saying, right, x, that will also get mapped here. Okay. So, maybe this is not the right figure. Okay. And if when this happens, okay, so yeah, surely this the number of ranges here should be less than or equal to the number of ranges here, right. This is a into mapping. So, then so for which sub ranges is it happening? It is happening precisely for the ranges such that x does not belong to R belongs to R. Okay. So, this range belongs to R and R union x also belongs to R, right. So, therefore, then I can write this as this plus this. These are precisely the duplicate elements that are making it happen. Right. So, I am going to add exactly those another set of these this will be added basically. So, then we will have the same so this equality will be satisfied. Okay. So, with this so I have written that. So, R is equal to R sub x plus R minus x. Right. So, our claim from induction hypothesis is what? So, this is the set of ranges that okay, so let us first look at this. So, this is the set of all ranges without the x part, right. So, this has one element less. Okay. So, one element less. Okay. So, from induction hypothesis, this is G delta n minus 1. There is one element less. Right. So, the claim is that the number of ranges in R minus x is bounded by this quantity. Right. How about this? Right. So, here what we can claim is VC dimension is delta minus 1. Why is it delta minus 1? Okay. So, VC dimension delta minus 1 means there exists some set, let us say set Z, okay, which means that Z equal to delta minus 1 and Z can be shattered. Right, i.e., all subsets of Z belong to R sub x. Now, so if that is so, then I claim that then all subsets so of Z union x can also be shattered. Why? Because note R prime belongs to the R x implies R prime belongs to R and R prime union x belongs to R by definition. So, I can also shatter Z union x, because I can generate all those subsets which contains x and does not contain x. So, that is the definition of the power set of Z union x. I do have all the subsets of Z anyway present in R, and now I have all the subsets of Z union x also present in R, because that is the way this was defined, right, R x was defined. And therefore, this quantity can be bounded by the first one. So, R x can be bounded by it does not have the element x, okay, and it has VC dimension delta minus 1. It cannot have anything more than delta minus 1, delta minus 1 and minus 1. Okay. So, the first term is g delta minus 1 n minus 1. The second one is g delta n minus 1. So, when you add them, the total number of ranges, the addition of that is according to our previous observation. So, number of ranges is less than g delta minus 1 n minus 1 plus g delta n minus 1.
So, definition of VC dimension says that it cannot be shattered for greater than delta minus 1.
Yeah.
So, should we prove that it is not, it cannot be shattered for delta? We are proving that it can be shattered.
No. So, we proving the by contradiction, right. Suppose the VC dimension of this was delta, it was more than delta minus 1, suppose it was delta. It means that for the original subset, original range space, it is delta plus 1, because I can generate all the power set of delta of this Z union x, right. So, by contradiction, the VC dimension cannot be more than delta minus 1. So, this is your g delta. So, we got this. So, it seems like it's a very clever proof actually. So, one needs to go over it a couple of times. So, although I have written this statement, these are true statements, maybe you have to just mentally sort of see why I can write this. So, in particular this you can do a case analysis, x belongs to r prime, x does not belong to r prime. So, this will come through. Right. So, so eventually what we get out of this is that if the VC dimension is bounded by delta, then the total number of ranges for a subset of finite subset of n points can be bounded by n to the power delta. So, it suddenly becomes a polynomial. Okay. Any questions about this? Okay, let's go ahead. Okay, so now let me establish. So, we started again. Let me just go back. We started with a definition called this shattering dimension, right? Shattering dimension is what? That if I take any point set of size m, then we can bound the total number of ranges by m to the power d for any m.
From short term, it follows that the shattering dimension is at most this dimension.
Yeah, something like that. Yeah.
Is there so this is the bound you are saying, or is there another?
No. So, this is basically what it is. That's all. So, there is a more precise statement that if S equal to x r has shattering dimension. Okay. So, one way should be clear, right? If something has a VC dimension delta, then we are able to bound everything by n to the power delta. And what does the shattering dimension say? That any point set of size m, we should be able to bound by some m to the power d. Okay. So, if the VC dimension is delta, so maybe I should write it actually. If S has VC dimension delta, then shattering dimension is bounded by delta. We do not want to argue the other way around. Okay. So, claim if shattering dimension of S is D, then the VC dimension of S is it D? Okay. This is a logarithmic factor. And what is a quick proof of that? So, if let us say this is the VC dimension, right. So, we are saying that the largest set that is shattered is of size delta. Okay. So, 2 to the power delta is the power set of this subset n, right, and that should again be somehow bounded by the shattering dimension, right. So, this is less than or equal to, so shattering dimension says what? Shattering dimension says that some polynomial, right, let me go back, this is shattering dimension, it is some m to the power d. Okay. So, let us say it is some constant, to be more precise, let us say it is some constant times n to the power d. Okay. So, this quantity 2 to the power delta should be less than some constant to the power, this is my, this is the size of the set, right, size of n. So, that to the power d is the definition of shattering dimension. Okay. So, this implies essentially delta is less than or equal to, you know, some is d log d. You just transpose this and you get that. Again, what is the motivation for all this? You know, in some, for some range spaces, it may be easier to argue about the shattering dimension, like I just argued about the trapezoidal map. Okay. It may not be immediately clear that the VC dimension should be whatever 4 or 5, you know, it may be much harder to argue about the VC dimension. What is the largest set of segments such that the trapezoid can actually generate all the subsets of that set of segments. Right. But we argued that that is 4, that is certainly bounded by 4. Let us say the shattering dimension is bounded by 4, and what this says is that the VC dimension then is bounded by 4 times log of 4. Again, so if one is finite, you know, some log of that multiple will also be finite. Okay. It is not going to be a very large number, it is pretty close to that. Okay. So, we are getting there, just a few more definitions before, you know, we go back to algorithms actually. I am only doing definitions. Okay. So, I think we will get to the algorithm only tomorrow. Okay. So, the other thing I am going to define is the notion of what is a dual range space. Nothing is complete without duality, right. So, dual range space. So, if S equal to X R is, let us say, the primal range space, then S star equal to R and X P such that P is to X. Let me illustrate that with an example. So, we have some points and these are my ranges. Suppose I am just drawing these ranges like this. Okay. Let me call it A, B, C, D, and P1, P2, P3, P4, P5, P6. Right. So, I can actually So, original range space we are talking about is basically the set of points, and these are the set of subsets, right. So, I can just write it as P1, P2, P3, P6. I can use a kind of a matrix notation to denote this whole system. Okay. So, what is I have 4 ranges, okay, and so P1 lies in S, that is just the incidence matrix. Okay. So, A contains P2 and P4 and P3, and the rest is all zeros. Okay. So, if I just write the incidence matrix, that is one way of representing the same range space, right. So, B contains P3, P4 and P5, P3, P4, well, I mean P6, P5 and then 0, 0, 0. So, I can complete this matrix. Okay. So, that is basically what I am saying, this is my primal range space, and the dual range space is nothing but the transpose of this. Why? So, we are saying in the dual range space my so I interchange. So, my ranges basically become my rows A, B, C, D, okay, and then X P are basically all those ranges that contain the point P, right. So, P1, P2, P3 all the way to P6. Okay. So, X P1, okay, essentially correspond to all those sets that has 1 in this column, right. So, P1, let us say what P1 lies in, P1 lies in D, okay. P1 lies only in D, nothing else, right, everything else is 0. So, X P1, what is X P1 then? Is just D, right. P2 is contained in A and D, right. So, A and D and 0, 0. So, X P2 is AD. Okay. So, these are my, so in the dual range space, so it is basically this is AB. So, S star, okay, is A, B, C, D, okay, and then some subsets of these things D, AD and so on and so forth, right. So, that is my dual range space. Now, clearly because the way I have drawn the picture, the dual of the dual is the primal. We just again transpose it back. Observation. S star star is S. What is the significance of this dual range space? Okay. So, we will I'll let me just write some couple of observations and then I'll just get to that. So, now there turns out to be some kind of relation between the primal range space and the dual range space in terms of VC dimension. Okay. If I can bound the VC dimension of the primal range space, I can bound the VC dimension of the dual range space and vice versa. Okay. So, in one direction it is this one, if S has VC dimension delta, then S star has the dual range space has VC dimension. Any guesses? Well, it is a pretty bad thing actually, it is exponential. But again I am saying what I have said before, and let me reiterate again, we are kind of only looking at the finiteness. Okay. So, if this is finite, that is finite, okay. That is what matters. And these bounds may not be tight. There are some proofs, which is a constructive proof. So, these bounds are not tight really, but it is not known whether it has to be exponential or not.
Less than equal to each other.
Yeah. If S has, okay, this is another statement, dual shattering dimension. So, if S has a dual shattering dimension, so of the dual space, so S star basically has shattering dimension delta. Okay. What does it mean? Then S star has VC dimension. So, what is the relationship between shattering dimension and VC dimension? VC dimension is bounded by d times log t, right. So, maybe I should write delta log delta, right. So, S star has VC dimension this, and according to the previous statement, and therefore, S star star that is equal to S, okay, has VC dimension 2 to the power delta log delta, which is about delta to the power delta. Again, it is only just establishing the the finiteness of this. Once you go there and we go there. Okay. So, let me stop here today, and the motivation for defining the dual range space is that we are getting to this the set cover problem actually. So, we'll define a very clever algorithm for constructing set cover in a range space, okay, that has bounded VC dimension. And when we do that, we will actually be constructing, okay, so there is another definition I couldn't do today, so I will have to get to that tomorrow, Epsilon-Nets basically. So, we will construct something called this Epsilon-Net. I defined this Epsilon-Net, right, it has to hit every large subset. So, the Epsilon-Net that we construct, okay, will be constructed in the dual range space, and therefore, we need these connections, okay. That is why I was building up with these definitions, all right.